So this project is not only an architectural and sustainability showcase, but as you hear today, but it's also a model of a team accomplishment. We use leading edge practices like partnering, interval costing, design assist, virtual design and construction. And the team was able to accomplish some amazing things, such as we stayed on track and were able to accomplish the project in a 30-month construction schedule. Cost growth from schematic design, this is an amazing stat right here. Cost growth from schematic design to the end of the project was only 6%, including all change orders. So it's pretty, that's a testament to the design team and the construction team to be able to grind through that. It was a complicated erection and shoring sequence that didn't allow the curtain wall to start until the building was fully erected, which is unusual, and if you watched it go up, you saw that it looked like a pretty rectilinear building, and then all of a sudden, you know, you start to see the different pushes and pulls on it. So, you know, all these things considered, especially the construction schedule piece, this was all done right in the heart of the COVID pandemic. And working through some of the worst supply chain delays and inflation and everything else. So just really an amazing feat by the team. So they're all sitting in front of us today. We had members of BU, KPMB, Suffolk, and VERTEX, and they were able to keep a sense of humor and enjoyed working with each other right up to the last job meeting. And you always say that there's good karma and bad karma on projects. And this is one of the ones that had really good karma, and you could see as the presentation goes on, everyone really enjoys each other. So I just want to make a few introductions to the speakers. I have Michael Swenson, Director of Sustainability for Suffolk Design. He's co-moderating with me. Dennis Karlberg, Associate Vice President for University Sustainability for BU. Paulo Rocha, he's a partner at LPMB, he's the architect. Josh Michaud, hopefully I hit that, Associate Principal at BR+A. Chris Kenny, Senior Project Manager at VERTEX. And then Frank Kramer, Project Executive, Suffolk. My name is Doug Russell, Director of Growth Strategy at VERTEX. Thank you. Dennis?
Thank you, Doug. I would like to just start with a little context for Boston University. We have we have 36,000 students and occupy about 15 million square feet of space on 3 campuses in Boston. The Center for Computing and Data Sciences is at the heart of the academic portion of the Charles River campus, where it can be the hub of data-driven academic endeavors. The project began with the need to support a critical academic and research initiative for the university, a need to create and create a space, an environment to bring students and faculty together across the university to focus on data in support of a better understanding of their endeavors. Data sciences is a highly competitive field and one in which Boston University believes it can lead. Data drives sustainable design. In 2017, Boston University's Board of Trustees approved an ambitious climate action plan, which set a goal for the university to be carbon neutral by 2040. Our plan also set out strategies to address indirect emissions and to address the impacts from climate change that can no longer be avoided. This building is a bold step in achieving these goals and leading the transformation to a more carbon-free future. I'd like to walk through the top 5 reasons. This is BU's most sustainable yet. There are more reasons, but I'll leave it at 5, and here we go. Reason number 1, resilient design. In the university's climate action plan, we set an elevation of resilience, above which all critical systems and equipment should be located. The Center for Computing and Data Sciences first floor is located 1.25 feet above our elevation of resilience. Reason number 2, net zero direct emissions by 2040. This graph is our greenhouse gas abatement curve. The vertical axis represents our emissions, horizontal years, starting in 2006. This is how we're looking at what we've accomplished and what we expect to accomplish in the Climate Action Plan. The shades of gray are fossil fuel emissions from various sources. First and most importantly, we will reduce emissions by 31% by 2032 through energy efficiency. We will shift from fossil fuel use to electricity for heating and cooling to enable the transition to renewables. We'll source renewable energy to match 100% of the university's electricity use. We will offset whatever is left over starting in 2040. Obviously, we want to keep that number as small as possible. And we will electrify our fleet over time. By 2023, this is hot off the presses, we released our annual report today. We have reduced our emissions by 65% from our 2006 base. But as you see, that little click to the right, that shows we've got the easy stuff done. Now we have the hard stuff ahead of us. This building represents the most impactful. This building is an incredibly great example for us and how we're going to meet our goals. If we designed this building to meet the very energy efficient standards of the Massachusetts Energy Code back when the building was designed 6 years ago, it would still produce nearly 1.4 million kilograms of CO2 equivalent annually. Using strategies to aggressively improve building energy performance, we reduce emissions by about 30%. Using the thermal mass of the Earth for geothermal heating and cooling, we eliminate the need for natural gas. There is no gas line connected to this building. That is bold. And that allows the building to be fossil fuel free. Switching the energy source from gas to electricity allows us to source that energy from renewable energy, from BU wind. That allows this building to be carbon free. I love this graph. The electricity the building uses is matched by the BU Wind project located in South Dakota. BU Wind came online in December of 2020 and represents the most impactful single step in meeting our climate action goals. According to the US EPA, this 205 million kilowatt hour power purchase agreement is the largest single active PPA by any college or university in the EPA's Green Power Partnership and puts BU in the partnership's top 100 along with Google, Microsoft, and Walmart. In 2021, BU won the EPA's Green Power Leadership Award for this project. So why did we choose South Dakota and not New England? Because we wanted to have the most impactful project we could find in actually reducing global greenhouse gas emissions. Since the climate doesn't care where our emissions reductions come from, we chose to find a project that would have the greatest impact. The project we found was a result of an RFP that netted 127 projects in the 4 dirtiest grids in the country. This project should be at least twice as impactful than the project located in the Greening New England grid. The project is located on 42 square miles of farmland in South Dakota, generating added income to the farmers who leased their land to the project while generating clean power for Boston University. The project is designed to match 100% of the university's electricity usage and has reduced our emissions by 53%. So, back to Boston and the Center for Computing and Data Sciences. We couldn't generate a meaningful amount of clean energy on the building, so we added solar on roofs on campus, three other buildings, totaling a generation capacity of 1.1 million kilowatt hours a year, equating to 23% of the Center for Computing and Data Sciences electricity usage. Reason number 3, the building is designed to create a healthy, productive, and pleasant place to learn and work. The spaces are interconnected with substantial access to daylight and views. Reason number 4, outdoor environmental quality. Green roofs step up around the building to create access to outdoor spaces on 7 levels. reducing the urban heat island effect, and providing rainwater retention. And they are spectacular. Reason number 5, we have reducing embodied carbon. This is our first project where we're really working to reduce embodied carbon. We were able to reduce the embodied carbon of this building by 6% by modifying modifying concrete mixes and extending cure times. So now that you've got a flavor of why this is BU's most sustainable yet, I'm going to turn this over to Paolo.
Thanks, Dennis. And just a slight correction, KPMB Architects, we want to work in Boston again. We love coming down here, so we get that all the time. Sometimes it's KPMG, sometimes it's LPM. Anyways, I'm a partner at KPMB Architects, and we are happy to be here and thrilled that we got the chance to work on this magnificent project. The Center for Computing and Data Science is located at the heart of the main campus at the corner of Commonwealth Avenue, situated between the brick Back Bay fabric and its limestone academic fabric. When Boston University put out its call for a design for the center, it asked for a dynamic addition to its campus in the skyline of Boston, a superb facility for teaching and research in a 21st century university, a facility that would showcase the university's rigor and excellence in data science, and, this is the most important, meet the university's ambitious sustainability targets. Understanding those goals, we set out to design a vertical campus with these design principles in mind. A center that is open, warm, and collaborative. It's a building for people because people are what drive innovation. From the beginning, we knew we wanted to reimagine what a tower could look like. It's composed of 2- and 3-story neighborhoods referencing the scale of the adjacent buildings along Commonwealth Avenue. Opening up at the corner of the site by lifting the tower creates transparency at grade and expands the public realm. Shifting the volumes creates research neighborhoods and departmental identity within the vertical campus. The 19-story tower anchors the corner site, pedestrianizes the ground plane, and creates a 350,000 square foot hub for the campus, bringing 3,000 students, faculty, and staff together daily. Porosity and transparency at grade were important to be able to engage with the public realm and invite the campus in. The ground floor is an extension of the public realm and open to the campus with areas for study and collaboration with a cafe and a few classrooms on display. The lifted second floor creates an urban porch marking the main entrance to the building. And you can see there's a blurring of inside and outside spaces. It was very important that the public realm extended right into the building. The spatial experience was paramount to our design thinking in order to promote human connection and well-being. A ribbon of movement connects the student-centric public space in the podium with research neighborhoods in the tower. The building is entirely walkable with an abundance of collaborative spaces throughout, featuring furnishings with low carbon emitting material. A collaboration terrace connects the ground floor and the second floor public spaces along Commonwealth Avenue. And a spiraling bold atrium stair featuring black steel and oak wood intensifies the opportunities for exchange and spontaneous interaction. This building was designed in the round. The core placement was strategically set back from the corner to allow generous public realm at grade. The tower volume is set back, emphasizing the street datum, creating a south-facing roof terrace that runs along the length of Commonwealth Avenue. Above the podium, the tower is broken down to 2- and 3-story neighborhoods that shift one structural bay as they rotate clockwise around the core. These shifts create outdoor roof terraces and break down the scale of the tower. The shifted volumes become research neighborhoods with outdoor terraces on each side of the building. The building has a total of 8 accessible terraces, each surrounded by greenery and spectacular views. The ability to access the outdoors and connect back to nature, the campus, and the city beyond was another important aspect of the design to improve people's health and well-being. The green roofs also reduce the urban heat island effect and retain rainwater. The minute you step off an elevator on any floor of the tower, you have a sense of place within the campus and the city. You're always connected back to the downtown core. We've minimized energy consumption by approximately 30% with energy efficient strategies including high performance envelope, enhanced HVAC, heat recovery, and energy efficient lighting. The energy efficient facade design is the most visible of these strategies. This building has two primary curtain wall types that are key to the design and function in different ways. Both are triple glazed. The first is the diagonal louvered facade. It has approximately 60% vision glazing and is located at the perimeter of deeper floor plates to drive light towards the core and provide the inboard offices with natural light and a sense of the outdoors. The louvers optimize thermal performance and lower solar heat gain during the cooling seasons. The second is the mirrored sawtooth facade. It has approximately 40% vision glazing and is located at the perimeter of single bay deep floor plates where natural light does not need to penetrate beyond one office depth. The mirroring of this facade conceals a more robustly insulated panel. With a focus on people's experience in the tower, key principles were established. One, to provide access to natural light and views, to create an abundance of collaboration space for formal and informal gatherings, to remove the hierarchical corner office in favor of open, bookable collaboration spaces open to all users, and to create a modular room to accept single, double, triple, and quad occupancy. The interior provides ample naturally lit collaboration spaces and whiteboard-clad walls throughout. Color infuses vibrancy to the tower floors and acts as a wayfinding tool for users. A stair connects all the departments, fostering connectivity, interaction, and collaboration. A large double-height flexible event space that supports various uses is located at the top of the building overlooking the Charles River. And adjacent to it is an exterior terrace with, again, spectacular views of the city and the campus beyond. Beyond its role as a university building, the building's bold presence has transformed both the campus and the city. The Center for Computing and Data Science provides a place for ultimate connectivity, delivers on sustainability goals, prioritizes the well-being of students, faculty, and visitors, and sets a high standard for design excellence. Now Josh is going to discuss the systems used to achieve our goals. Josh?
Hello, everyone. I'm Josh Bashad. I'm a mechanical engineer at BR+A Consulting Engineers. I'm going to go through a little bit of what we did, hit some of the highlights. For us, the first thing we look at, there are kind of three pillars for us, right? We heard a lot about the off-site renewables, energy efficient systems, and of course, eliminating fossil fuels in general. Well, I'm going to talk a little bit about the how. You heard the statement, this building is for what? It's for the people, right? The people create one of those loads. One of the first things we worked with KPMB is we asked the users, what are they really doing here? Because I hear the word data sciences, and I think there's going to be a significant amount of load inside this building. The by-the-book approach would have had us designed to 4 watts a square foot that I would have had to cool. But we've actually did metered data to show and support the fact that we're really not going to be anywhere near that number to help us reduce that load overall. We designed for 1.2. I think we're really operating at more like 0.65 in your individual office spaces. Then there's the building facade. Thank you to KPMB for delivering a big glass box to an engineer who has to cool it. Love it. But from the jump, they always knew as well, this had to be something that was, one, tight construction, and we had to target how do we reduce this load, all by getting the effects that you want from having natural light. So we worked with KPMB of optimizing these louvers. It might seem like, oh great, we've reduced it by 30%, but that could have just as easily been 20% if they were at the wrong angle. So we talked a lot about where does this make the most sense, and in which locations does it make the most sense, and we actually made some changes based off of what the original intent was around the building as it worked. And then we decoupled systems. Every building needs ventilation air put into the building. Every building. But it also comes from a central system that tends to use one of the biggest chunks of energy in the building itself, right? These are large systems that use big static pressure. So we wanted to reduce that. So we put in the ventilation air that we need, but at the zone level, we use a hydronic system because we can move more BTUs more efficiently at the zone level by using hydronics. We used active chilled beams, that's the stuff around the perimeter that you see, and we use fan power boxes. So if we needed more load out of the beam, we didn't just push more air from a big central system, we moved air from our plenum up above and pushed the beam harder to get the load we needed out of each of the individual spaces. And then there's the central system itself. This one actually has a major role for what we did in this building. It's a dual-wheel DOAS, our dedicated outdoor air system. What we did here is we looked at, we have a dehumidification load. Well, this system gets us a much lower dew point, hopefully not being too technical here, but it essentially reduces our dehumidification load at the zone level for free because it's active through the second wheel, which is desiccant. It also increases the discharge air temperature that we're putting into the building. Usually 10 years ago, or when we would have started, 55 degrees, we're doing 65. So that reduces the reheat load. Again, the heating load is what you're trying to electrify the most, and it's the hardest thing for us to do. So one smart decision had a major role in massive energy reduction inside the building. Now we put all these things together, and while we started rethinking this building and what we could do, we were asked this question about how do we actually electrify? How do we make it that we don't put gas in this building? We will not bring gas to this building. How? So you see on the bottom here, this is just a very basic diagram, but geothermal was the how. So we started talking about that. Here what you see is our site. Student housing, a laneway, Sargent College, and our building. People think geothermal, they're going to ask, how many wells did you need? We said, we need 100. And we all said, how are we putting 100 wells on that site? We ended up with 31, right? So now you start to say to yourself, how does this make sense? How can you do 31 to 100 and get the same bang for your buck? This is how. We asked how deep could we go for the building. As you see the graphic develop, you'll see we go pretty deep. 1,500 vertical feet deep into the ground, twice the height of the John Hancock building, for those of you who know the Boston landmarks. If you just look at the scale of what's going on there, it's pretty impressive, right? When we're heating the building, we're essentially cooling the ground. When we're cooling the building, we're essentially heating the ground. And what we're doing is we're swapping that energy all year long, right? We're trying to balance our well field. We're going back and forth. And we're going to learn now even, as we learn what the building's really doing and what the earth can really do, we tune this over time. In addition, when someone says we're going 1,500 vertical feet and it's not the norm, you start to ask yourself, is there any way we can get more BTUs per linear foot? So this is called a Rygan bore. What you see with the helical design is essentially increasing surface area. More surface area, more BTUs per linear foot. If you're going to invest in only 31 wells, and you're going to hear more about the drilling process for that in a few, how can you get more BTUs to get a more bang for your buck, if you will, for the building? So we went that further step on this as well. I don't want you to pay attention too much to all the crazy squiggly lines here. The big piece is what's in red. Our geothermal accounts for 90% of the operating hours for heating load in the building. 10% of the time is the only time our boilers, which are electric, not gas-fired, will come on. And we've seen that work. We've also seen our boilers come on in a very, very cold state, not much more than what we have here, in somewhat of an emergency situation, if you will. The other part to talk about is, based off of where we started to where we landed, this system took less space inside the building. So what owner doesn't want to give the space back to the people that it's trying to serve? Would you rather I need an extra 1,000 square foot of mechanical space that no one really gets to see unless I'm up here talking about it? Or would you rather have the users actually be able to use the space and act and do something with that, right? And finally, our cost comparison. It's a little misleading because it just says geo on the right, but the intent is to show you that When we did this analysis relative to what we would have designed in general for a standard high-performing building, less than 1% increase in construction cost. Pretty impressive feat, and I think well worth the money. Now I'll hand it over to Chris.
Thanks, Josh.
Yep.
Doug alluded to it in his introduction, but it takes a committed team of people to accomplish the aspirational sustainability goals for a project within a tight schedule and budget. One of our first acts as the owner's project manager was to organize a multi-day partnering event with an outside facilitator. Participants included the owner, both leadership, but also their facilities and operations personnel, the design team with the architects and their consulting engineers, and the construction manager with cost estimators and their field staff. The goal of these sessions was to create a common culture among the team and instill a sense of individual accountability to the team to facilitate working together. During our group working sessions, a tennis ball would randomly be tossed around. You had to catch it and toss it back. You did not want to be the one to let your group down by being the one that dropped the ball. Small groups met in breakout sessions to brainstorm a list of priorities and project concerns and challenges. Then all gathered as a larger group to reach consensus on the most important potential risks facing the project. Then the group identified strategies to mitigate against these risks. One strategy to mitigate against the risks was to establish task forces to dive deeper into specific topics and the issues raised. This was a key outcome from the partnering sessions, but also a key contributor to the overall success of the project. Different task forces focused on different areas. There was site logistics, there was iterative cost estimating, there was design assist for early procurement, and then most importantly, geothermal systems. Each task force developed their own action plans and determined who would be engaged, the frequency of their meetings, what the desired outcomes for those meetings would be, and then how to track and report progress back to the project team. The geothermal task force was fundamental on executing the sustainability on the project. This group engaged not only the design engineers, but also a drilling consultant, subcontractors, material vendors, legal counsel, and city officials. This geothermal task force analyzed well locations to coordinate with civil utilities, well depth and verticality to confirm temperature profiles, and the what ifs to plan for any future circuit failures. This successful task force engagement resulting from team partnering sessions provided guidance to project leadership to make informed decisions. One such decision was to undertake a test well program, which Frank will take us through now.
That BU was going to do the geothermal. You know, we thought we were the geothermal experts because we had done a project with 400, 800 foot deep geothermal wells. This project, without a doubt, took it to a different level. 31 1,500 foot geothermal wells in downtown Boston is a significant undertaking, particularly when it's on an urban site, on a very active campus, that is hemmed in on every side by either student housing to the left, an academic building to the north, Com Ave to the right, and and we had Granby Street right on the bottom of the page here. So when we came out of the gate in conceptual design, what was absolutely essential to make sure we stayed on budget through GMP was getting the right cost that would carry through the project. So step one was engaging the geo and site communities to help us establish the right budget going in. The next piece of the puzzle was to make sure we understood the logistical challenges that would come into play with a project of this size, and the risks. So this is where we got into the test well program. And we did a couple things. We canvassed the Northeast to find qualified well drillers that would be interested in doing a project of this scale. And we also went so far as to go into Texas and talk to the oil drillers because there was kind of two studies we did. One was drilling the traditional way, the way you would typically do it for a project like this, or the way they do it down in the oil fields, which is directional drilling. Very expensive, cost prohibitive, would not work for this project. So we went out to the market locally and got bids for the test wells. And that's where we made our first really important decision, investment in the project. And that was, instead of awarding the test well to one firm, the geothermal task force decided we're going to award one well to each of the bidders. So we had 3 different well drillers come to the site and drill a well. So you can see here, this is when we were kind of like planning out the wells, but there was 3 test wells that we did early on. And this was really to get the lay of the land. So we got 3 different perspectives. We had 2 drillers that drilled with air and 1 that drilled with water. Gave us a chance to get our arms around the logistics and the challenges to get to that 1,500 foot depth. 1,500 feet is atypical. So when we were out probing the market for interested drillers, some of them just shied away because a lot of them are not comfortable going past 1,000 feet. Once you get past 1,000 feet, you got to bring in specialized equipment to drive that well down to that depth. And as most of you know, in Boston, the rock's at about 200 feet. So on this site, 200 feet, you're at the rock. So then you're going 1,300 feet through the rock to get to the bottom of that well. Okay, so we learned a lot during this test well program, and ultimately we picked a partner. And I'm just going to go back a page that'll just kind of give you the aerial. So on the job, this is when we're in the production well mode. That green drill rig that you see there that's the one that's drilling to depth. So we would come to the site with we called it the red rig. That would drill and case 200 feet. We'd grout casing 200 feet into the rock. And then we'd bring in this green rig here and we'd drill to depth. The big thing we've learned in the test well program is you are generating tremendous amount of water in these wells when you're down into that ledge. So, when we're doing deep foundations or deep holes in Boston, we know the water is about 14, the groundwater is about 14, 20 feet below grade. Here, we're cased all the way into the rock. Then we start drilling to 1,500 feet. When you hit a fissure, drilling those drills, you could have water coming out of that hole at 200 gallons per minute. So we have to, at the backside of that green rig, we create kind of like a retention pond that water's pouring into, which is then pumped into, you can see right below the A, we've got a series of 3 frac tanks right there. First one is a wear tank, so we're pumping water through these tanks. All the suspended solids are floating to the bottom. We're filtering that water out, and it finally comes out at the back end, and then we can send it into the storm drain system. But to the upper right there, you can see that sedimentation pond. That has to be created early on because what we're ultimately going to do as we're filtering this water through here is we're sending this vac truck that you can see below that retention pond. That's going over to those frac tanks. It's sucking out all that sedimentation and is dumping it into that pond right there. And that pond right there is just the residual out of that frac tank. So we're constantly recycling the water, treating that water that you can see in that pond with dense grade and cement to solidify it so we can truck it off site and make way for the next group of wells. I'm happy to say that this particular operation went extremely efficiently. We were able to drill 31 1,500-foot wells in this very tight spacing without any collisions and with really spot-on verticality, which is absolutely essential for Josh's system. And then ultimately we build the building after we drill all these wells. And once the building's built, then we tie the networks of piping together that feeds the system inside the building. So I'm going to turn it over to Dennis, who's going to talk a little bit about project visualization.
Thank you, Frank. Let's go fast through those slides. There we go. So as you've heard, this building is about providing collaborative spaces for our students and faculty to connect at the intersection of data that supports their individual studies, individual fields of study. To accomplish this, we needed an extremely collaborative team. Another way this collaboration is expressed is through the sustainability wall located at the east entrance of the building. The interactive LED screen hosts 15 videos, several you've seen here today, tied to data from the building. We're collecting data from over 450 points within the building, and we're displaying it on the wall as the videos are going, so you can see in real time how the building's performing. I'd like to really note we had a phenomenal team, both for design and construction and all the administration for the project, represented here by KPMB Architects, Suffolk Construction, BR+A, and VERTEX. KPMB, when they won the competition back in 2012, 13, 12, had assembled this team. And they were able to deliver the building that we got at the end of the day, but the university was not ready for the building we got at the end of the day. In 2013, 14, the building went on hold, design went on hold for several years. In 2016, the Board of Trustees asked us to put a climate action plan together. They approved an ambitious climate action plan at the end of 2017. 2 months later, the team was reassembled and asked to do a fossil fuel-free building. And they delivered. They were ready to go. It's great. So we have achieved LEED Platinum for this building. Oops, hold on. One more, back here. LEED Platinum for the building with 10 points to spare. I would like to say a few words about leadership. If we hope to build a more just and sustainable future for our species and others, we need to work together. We hope that Boston University's sustainability leadership and collaboration with our colleagues in the community, with the city, state, and more broadly, will help us all move forward. As Mayor Wu noted at the ribbon cutting, this building really sets an example across the entire country for how to think about integrating our climate obligations. Thank you.
Thank you, Dennis. We'll give us a few seconds to transition into the panel, and we'll keep going. Excellent. So thanks again, everyone, for joining us today. This first question will be for Dennis and Chris. It's difficult at the beginning of the project to get everybody on the same page. So what were the primary challenges faced in coordinating various stakeholders for buy-in to this net zero vision, and how did you overcome these challenges? Dennis, we'll start with you.
Well, obviously we had a great team, and I think, let me just kind of go on one tangent. The geothermal was a big question for us. We've done geothermal before, but not at this scale. And we wanted to be confident that we could actually do this. So KPMB has done a few geothermal projects. We went to visit those. And then we did the test well, which that was a brilliant move to have 3 different contractors doing 3 different technologies and really looking at time it takes to do these wells. We were budgeting 2 weeks per bore. The verticality, how that was a critical component to this, as well as what the thermal capacity really was. So it was really sort of an iterative process and an integrated process. I think that was key to success.
Absolutely. And Chris?
Yeah, thanks. Just picking up on what Dennis mentioned, there was some apprehension on the operations side when we started this project about how this big building was going to be managed, maintained, and operated. We did three things. First, Josh and his group did multiple page turns to take them through piece by piece to kind of explain what was intended and showing them that yes, it's cutting edge, but this is equipment that they're used to dealing with. The second was a follow-up meeting with the contractor and all the subcontractors and their subcontractors to go through in more detail the specific pieces of equipment that have been submitted and selected and how each system was going to work together. And then the third thing was taking the commissioning agent and extending their contract out for 18 months so that they would make sure the building that gets handed off is completed and operating as designed.
And just to hit on those last 2 points, I think it's really important, even though these activities, commissioning facilities are happening at the end, to bring them to the forefront of the conversation and be able to make sure that everybody's on the same page. These next questions for Paulo and Josh. Paulo, I'll start with you. What significant lessons were learned from the implementation of the net zero energy strategies in this project? And if this project were built today, what would you change?
Nothing. That's a very tough question. It's like, if you had a child, and what would you do different? A lot. Would you? Maybe. Actually, I can answer that question probably better than this question. No, you know what? I don't know that there's this, I'll let Josh talk about the system, lessons learned, but the biggest lesson, I think you're hearing it from everybody, is you need a vision to build a project like this. You need a vision that's a client that wants to do a net zero building, which doesn't come very often, and we are lucky enough to be part of it. And with that vision, you need a champion, you need great consultants, you need a great team. So we assembled, I think, the best team we could to do this project. And the lesson learned is you really need to structure your team for that specific project and those needs, and be able to fulfill that, and come together early and discuss the strategies on how to be successful. So if you listen to everybody, everyone's got a different point of view, you will inherently get to the right solution.
Absolutely. Josh, did you want to talk a little bit about the systems?
Ditto. And yeah, we've got two. One we actually enacted during design was we were close to issuing CD GMP level documents, like finishing, and internally we said, we've overcomplicated this, and you're delivering to an owner who hasn't done it yet with systems that they're known. These are not new systems, but when you haven't seen them, everything feels new, it's different, right? So we actually kind of did this all stop, and we just said, hey, by the way, there's nothing wrong with the current design, but we can simplify this. What do you think, right? So just kind of going through things and keeping things simple by doing that, that was a strategy, like this lesson learned to say, don't get beside yourself, like keep talking to the people. If you've got that relationship, then it works, right? It's not always easy to do, but you kind of had to do it. The other piece is, like, if we had to build this building right now, we would not even be able to put electric boilers in the building, right? That would not be the decision we would have made. We would have pushed harder on the load reduction, probably hoped for less glass. We would have probably had to leverage a different type of heat pump potentially if we did have the same load profile, or maybe it would have been another 15 wells. That last 10% I talked about earlier, it's the hardest 10% to get, right? It's the hardest to get. So like the scale of what you need to do would have been pretty significant to the project. So that's kind of what we're doing now as well, and our legislation is forcing it. You wouldn't be allowed to do it.
And I think that's an important point here in Boston, but as we have a national audience, see places like California also getting up to speed with those regulations. How do we meet those new requirements? How is technology changing to meet those needs?
Just on the glass. I mean, on average, it was about 50% vision.
Yes, we did.
So Yeah, you pushed us. But that's
you're
pretty,
absolutely right.
that's a big. It's not when you say all glass. I just don't want people to think it's 100% vision. That would be hard to achieve what we did.
Dramatic effect.
Right.
You shouldn't have had the architect and the engineer sit next to each other.
This is how it works.
Next question for Frank and Chris. Frank, we'll start with you. What strategies were employed to mitigate the risks associated with the geothermal system, cost overrides, schedule delays, compatibility with the existing site, and what lessons learned could you apply to future geothermal projects?
Test wells. That was really key, as Dennis mentioned. That was a big part of it. I think when we came out of the test wells, we knew that verticality was critical, right? And with how tight these wells were together, we had to avoid collisions. When you're drilling 15 feet, if you start deviating significantly, you can clash with another well, and then you're starting all over again, or we're certainly going to incur more costs. So a lot of risk with subterranean work, so we knew we had to set aside some budgets for this event. So we had about $500,000 set aside. But on the flip side, what we did is we incentivized the drillers. And when Dennis we talked about 2 weeks roughly per well. One of the big things we talked to the well drillers about after we did the test well program was this is all about, on any project, it's safety, quality, schedule, right? We're not trumping quality for schedule. So we incentivized the drillers where they could earn additional fee by keeping these wells straight and staying on a very reasonable schedule so that we could make sure that we had a successful drilling operation. At the end of the day, we got the verticality and no clashes.
Chris, anything to add?
Yeah, the test well program really gave us the confidence to be able to do the production wells with the incentive program. I think we learned a lot. We evaluated them based on noise because it's a campus that's activated. Time it took because we wanted to get it done as quickly as possible. And the third was verticality. So that incentive, which ended up $200,000, might have been the best money spent on the project. All but 3 or 4 of the wells were within the incentive program. So we ended up with straight vertical wells in a timely manner. So success.
Excellent. Yeah, high percentage of success. Last question, Dennis. So what's next for BU on the road to decarbonization?
Great question. We've learned a lot from this building, and it's also given us a lot of confidence to understand what it takes to do this work. So we're continuing to build new buildings, and that's the easy work. It's not easy, but it's the easy work. The harder work is decarbonizing our existing buildings and taking, the 10% that Josh was talking about with electric boilers. If we can look at existing buildings, add where we have low temperature hot water, add air source or ground source heat pumps, depending upon the location on campus and the possibility of an ambient loop sharing thermal energy with other buildings, we could do ground source or we do air source, but leave the existing systems in place for now, for that last 10%. That we can get a lot more done that way. And this, by the way, is Dennis getting over his skis as usual. That's what I'm seeing we're going to need to be, that's how I see our approach. We are beginning a process to plan an update to our climate action plan, which we envision to do every 5 years. We're a little bit behind schedule on that, but we do need to do this and decarbonization focus. And not changing our goals, still 2040, but that abatement curve, what does that look like with what we've learned? And also what we can do to take advantage of the IRA and other incentives that are out there that weren't out there before. So it's really kind of an integrated approach that we need to be looking at.
We're excited to see how it turns out. At this point, we'll take questions from the audience. If you're online with us, we have folks monitoring the chat, so please feel free to ask questions. And if you're in the audience, feel free to raise your hand. We'll come around with the mic. No questions here in the audience. No questions online. So I want to thank everyone for being here today in person, also online. For those that are in person, we do have refreshments afterwards, so please stick around with us. But before we get to that, please give a round of applause for the team here. Thank you, everyone. Have a good night.
Excellent.
Thanks for coming.
Absolutely. Doug?